Good afternoon. Today we're going to cover the last topic for the statistical mechanics course, and it's the heat capacity of solids. So we're going to examine the heat capacity that's associated with the lattice vibrations of crystalline solids. There are two basic experimental facts that you should be aware of. Near room temperature, the heat capacity of most solids is close to 3 times K, Boltzmann's constant, per atom, which reflects the classical law of Dulong and Petit, which states that the heat capacity is 3Nk for, if I have a solid consisting of 3N atoms. The second observation is that at low temperatures, experimentally, heat capacity should decrease and vanish as T approaches 0, as is dictated by the third law. The experimental data indicate that the behavior is on the order of alpha T cubed plus gamma T, where alpha and gamma are constants. So that's what's observed experimentally. Now, of course, the idea is to see if we can come up with a theory that would reflect why we have these experimental results. Classical equipartition of energy theory would say that, of course, the law of Dulong and Petit would work at any temperature, but that can't be possible because we know that at absolute 0, the heat capacity must be 0. It can't be a constant all the way down to 0. Where we'll start, we're going to cover 2 models, and we've talked about one of them before, but in a completely different context. We've discussed the Einstein model for lattice vibrations. That was done when we studied multiplicity very early in the course. We weren't that worried about the physics that Einstein was suggesting. We were more interested in using it as a nice example of multiplicity. But now we want to look at the physics. So it was in 1907, this is after his big papers on special relativity, photoelectric effect, and Brownian motion. That was in 1905. But in 1907, in a paper, Einstein attempted to explain experimental measurements of heat capacities. So as he did that, he made some assumptions and created a model that, as you'll see, will be qualitatively pretty good, but quantitatively will leave something to be desired, and we'll have to do a model that follows that, a model attributed to Debye that does a much better quantitative treatment. Nonetheless, let's go through again the assumptions of the Einstein model. He assumes that he treats a crystal like an N-atom entity. It has, in 3 dimensions, 3 N independent oscillators, and they vibrate. The assumption was they all vibrate with the same angular frequency omega. This turns out to not be a great assumption, but it will help us as we go along. This is probably inspired, in fact, I would put money on it. This is inspired by Planck's black body radiation treatment, in the sense that energy is quantized again. So what we expect is that, in addition to that, of course, Einstein 2 years earlier had come up with the photoelectric effect, which also was an indication of the quantization of energy. So, let's do the following. We were exposed to the Einstein model early on. Let's write it this way. Let's talk about the energy of these oscillators as being h bar omega, similar to the Planck formula. We can write the equation of motion for an oscillator the following way. The second derivative of r with respect to t can be written as minus omega Einstein we're using times r. As I said, we're going to assume that they all oscillate with an angular frequency omega. And we can decompose r into its x, y, and z components. So a solid of n atoms, you might remember, contains 3n oscillators. Remember, an oscillator is not an atom, right? It's a mode of vibration. As we will mention later on, we call those modes phonons. Now, this is a gross oversimplification because there really is a strong coupling between atoms, and the other atoms do provide a restoring force for any given atom. But as a first approximation, this really isn't too bad. So the oscillators have to have energies corresponding to discrete states. And we're going to use the canonical ensemble. Let's look first at the partition function for one oscillator. I can write it as r equals 0 to infinity e to the minus beta e times r. The idea is that we're going to use one atom or one oscillator as the system and the remainder of the solid as the reservoir. That allows us to use the canonical distribution. So I can write this as sum r equals 0 to infinity e to the minus beta h bar omega times r plus 1/2, the energy of a harmonic oscillator. I'm going to do a little substituting here. I'm going to write this as e to the minus x over 2, sum r equals 0 to infinity e to the minus x times r, where I'm defining x as beta h bar omega sub e, or if you like, h bar omega sub e over kT. This is the familiar ratio of the vibrational energy to the thermal energy. Now, for any function that looks like 1 over 1 minus t, where t is small, I can write that approximately as 1 plus t squared for absolute value of t less than 1. So with that in mind, I can write my single particle partition function as e to the minus x over 2 divided by 1 minus e to the minus x. I want to calculate or determine the Helmholtz free energy from this expression. Remember, Helmholtz free energy is minus kT times the log of z, in this case the single particle partition function. I can write that then as h bar omega sub e divided by 2 plus 1 over beta times the log of 1 minus beta e to the minus beta h bar omega sub e. Furthermore, the mean energy per oscillator, we'll write as E bar minus d log C1 with respect to beta. I can write as minus d beta times minus beta times the Helmholtz free energy. Put that all together, I can write then my mean energy as 1/2 h bar omega sub e plus h bar omega sub e divided by e to the beta h bar omega sub e minus 1. Recognize the first term in this expression is the 0 point energy of the oscillator. That means it's going to have this energy even down to t equals 0. Since energy is an extensive quantity, we expect that I can write the total energy of this system as n, however many oscillators I have, 3n that is, times the mean energy for one oscillator. I can write then my heat capacity as a function of t as the derivative of the energy with respect to t at constant volume. And also, to do that, I can do a chain rule, and I'm going to write that as dE d beta at constant volume d beta dt. That will give me 3nk x squared e to the x divided by e to the x minus 1 quantity squared for my total heat capacity. We're going to write this slightly differently. We're going to write where x is equal to, as we said earlier, x is equal to h bar omega e over kt. I'm going to write that now as capital theta sub e divided by t. We call capital theta sub e the Einstein temperature. And it's equal to h bar omega e divided by k. It's interesting to take this expression and to look at it at high temperature and low temperature limits. Let's do that next. Let's look at the low temperature limit. In this case, for temperatures much, much lower than the Einstein temperature, or if you like using the variables x we had before, x is much, much greater than 1. That means e to the x is also much, much greater than 1. If I look at the expression, CV then is approximately equal to 3 nk theta e over t squared times e to the minus theta e over t. So this is t much, much less than the Einstein temperature. So that the good news about this is that as t approaches 0, CV approaches 0. So qualitatively, this is correct. And it's not exactly a match to the data, but it at least comes up with an answer that the specific heat or the heat capacity would approach 0 as the temperature approaches 0. The better news is that in the high temperature limit, where T is much, much greater than the Einstein temperature, or X is much, much less than 1, we recover the law of Dulong and Petit. So in other words, CV will approach 3nk. And you can see this fairly readily because look at, we have x squared e to the x divided by e to the x minus 1 quantity squared. At low temperatures, I can expand the e to the x, and of course, that's going to turn out to be 1, and therefore, I will recover the law of Dulong and Petit at high temperatures, room temperature or above. This is also in keeping with what we would expect from the equipartition of energy theory. At low temperatures, if kT is much, much less than h bar omega e, we say that all the oscillators are most likely in the ground state. Those oscillators will make no contribution to the heat capacity. We say that these degrees of freedom are frozen in. So how does this compare with experiment? Again, the agreement works fairly well near room temperature, as does Dulong and Petit. But with a closer look, we're going to find that experimentally, CV goes as T cubed as we get to lower and lower temperatures, not exponentially the way this is indicated. So the Einstein model, although it gives us some qualitatively correct things, we need something a little bit better. And so it leaves something to be desired. What we'll do then, we're going to move into an improvement on the Einstein model called the Debye model. A couple of things I want to talk about, though, before we get there. First, when we talk about these oscillators, I mentioned this term before, but I want to bring this up again. Particularly those who are going to study solid state physics or condensed matter physics, we often call these oscillators phonons, akin to the electromagnetic equivalent of photons. So when I examine the energy of lattice vibrations, I have an expression for a system with 3 N oscillators that looks like this. We know that the first term is attributed to the ground state energy. And the second term, of course, looks a lot like what we would get from Bose-Einstein statistics, which is exactly right. Phonons are bosons. And the phonon represents a quanta of vibration. So don't be confused. We're not talking about particles, atoms vibrating. We're talking about the oscillations themselves as phonons. Okay, so don't make that mistake. If you want to pursue this further, I recommend textbooks by Ashcroft and Merman or Stephen Simon. He has an elementary solid state physics textbook and does a very nice treatment of phonons in there. One of the great things about learning statistical mechanics is it gets you much more ready to pursue topics such as condensed matter physics. What we'll do in the next video is to use phonons and normal modes to introduce the Debye theory for solids. And that will be, or for heat capacity of solids, and that will be a much more accurate treatment of vibrations. Thank you.